What have we done? We've spent the last couple of weeks, 3 weeks, I don't know, telling a story about people seeing little lights moving around in the sky, trying to figure out the crazy stuff they did, trying to make sense of it for all kinds of reasons, going through all kind of turmoil of all different models down through the centuries, the millennia, kind of culminating in 3 weird empirical laws, and then Newton creates the universe, or finds the first universal law that governs the heavens and the earth. And what we found out is what the universe is all about is love. Nice sappy thought, but you know what? That's kind of what this is, because this really says that every object and every other object in the universe pull on each other. Everything's attracted to everything, and this is how hard, and it depends on how much mass they got to love each other with, how much there is to love, and how far apart they are. Distance makes the heart grow less fond. See, if they're further apart, it's weaker. So we've been through all this. We found that there's some things some really amazing stuff we figured out. You know, we found the mass of the Earth. And if you know the mass of the Earth, which is just under 6 times 10 to the 24th kilograms, you can divide by the volume of the Earth, get the density of the Earth, and know kind of what the Earth is made of. We found the mass of the Sun. Now, I did not make this point the other day, I don't think, but I will now. The Sun turns out to have about 330,000 times the mass of the Earth. And that kind of means who you think goes around who mostly. Yeah, I think the big one is the one that gets gone around the most. Though actually you could say that Ptolemy was 1 part in 330,000, right? Because sun wobbles a little bit when the Earth goes around it. In any case, we're figuring out all kinds of things. Let's see what else here. I have a list. We explained Kepler's laws. We united the heavens and the earth and showed they're all under the same laws. Yeah, we found the mass of these things. Ooh, there's one more thing I want to find the mass of. Since we got the power now to do this. There's this thing called the Milky Way. Maybe you've seen it. Most of you haven't. I've taken polls of students before, and most people don't even know what it is other than a candy bar. You go out on a nice, clear night out in the country somewhere, especially good time is in the evening and early fall. It's a great time. You'll see this band of light across the sky. It's the combined light of millions of stars, even billions of stars, and we live in it. Basically live in a giant pancake of suns, stars, solar systems, star systems, whatever you want to call them. A lot of them. Now, I'll tell you what, I'm going to tell you a couple pieces of information. We're going to figure something out kind of quickly. I might do one of those like pause things. Let me tell you a couple things. One is that the sun is found to orbit the center of the Milky Way galaxy. There's something special there in the center, too, I'll talk about later. But in any case, we orbit the center of the Milky Way. And it takes a period of 250 million years. We know that by observing motions of other stars. It's a long, long story. I don't even know all the parts of it. But in any case, we take about 250 million years to orbit it. And what do we orbit? The center of the Milky Way. By the way, the Milky Way looks kind of like this. It's like some giant whirlpool-like thing, like that, like a giant hurricane in space with a big central bulge of stars there. There's the center. And we live about 2/3 of the way out toward the outside, and we orbit the center of the Milky Way. 250 million years. And the distance to the center of the Milky Way is about 28,000 light years. That's not an amount of time. That is a distance. A light year is the distance light goes in a year. The speed of light is about 3 times 10 to the 8th meters per second. You know that there are, about 365 days in a year. There's about exactly 24 hours in a day. There's 60 seconds in a minute, and 60 minutes in an hour. You could use this times this to find what a light year is. It's about 9.5 times 10 to the 15 meters, I think, some crazy distance. It's actually about almost 6 trillion miles. And then you could take that and multiply it by 28,000, and you get the distance to the center of the Milky Way in meters. I'm trying to remember what it is. It's big. You can figure it out. And then what you could do, since I'm just like giddy with my power here, is we could find the speed that it's going around, by getting the distance, 2 pi r. R now. R is this huge, what we just saw, over t, the period, which you can do all this stuff and turn it into seconds. So if you do this and get some number of meters per second, it's a lot. It's maybe 100 and something thousand meters per second. It's that kind of speed. And then you could actually use V equals square root of GM over R, like we did before. You could get M by itself. M would be RV squared over G, and you plug the things in, you get the mass of the Milky Way galaxy, or at least the part inside our orbit. The answer to that is something on the order of 10 to the 41st kilograms. It's something times that. I didn't just figure it out. I've just done it a lot before, and it's on that order. And that is equivalent to like 100 billion suns. Look what we just figured out. We just figured out we live in a giant community of about 100 billion suns and solar systems in our galaxies, one of many, many scattered across the universe. I will invite you to try to plug in the numbers and figure that out. I don't know to what extent I'll hold you responsible for it. Oh, here's my eraser stuff. But hey, give it a try. You got the power. Anyway, so yeah, you can figure out amazing stuff like that. Massive universe, all that. I'll leave this up here for reference for a minute, maybe. So what else can we do? What other wonders of the universe could we describe? Oh, I know. Here's a thing that, remember the characters in the story? There was Newton, of course, but he also, had his enemy, his nemesis, Robert Hooke. There was Christopher Wren, the guy who designed a bunch of stuff, an architect. And I mentioned Edmund Halley, and you've heard him because of a comet. The reason the comet got named after him is because he used this law that his friend Newton had come up with to predict. Let's see, the comets were seen occasionally, these mysterious things that appear in the heavens and appear for weeks at a time. And by the way, the whole name for a comet was actually Aster Cometis, if I got my Latin stuff right. Aster, asterisk, star, comet, comb in your hair, you can comb mine. It's a hairy star. A comet is a hairy star. So what would happen, these hairy stars would appear from time to time in the sky. And I've seen about 5 of them in my life, about 4 of them, including Halley's, were fairly decent to look at with the naked eye. Others I've seen with telescopes. You don't see them streak across the sky all of a sudden. You see them rise and set with the stars, but kind of move kind of quickly compared to what planets do. Every night they're in a little different place significantly. And so they're moving relatively fast in that sense. And they have this tail thing that always points away from the sun. It doesn't show which way it's going. Comets aren't necessarily going that way. It could be going that way. It could be going that way. It could be going that way. The only thing I can tell from this tail is that the sun is over here. That's a bunch of stuff about comets. I got a lot to say. You know what? Whenever a comet would show up, there would be something like a pestilence or a war or a plague. And people thought that comets were responsible or symbolic of those things, or omens or portents in the heavens. There is a comet there's one coming that might kind of brighten up and possibly become naked eye. I'm not associating it with the coronavirus. That's not my point. But I will say this. Bad stars, evil stars are called disasters. Yes, that's what a disaster is. It's an ominous, evil star because people would see comets appear. Anyway, back to the story. Halley had noted in historical records that there seemed to be a disaster one of these, about every 75 to 78 years. And he realized that, in fact, that could be, that these things could be not one-time events, but repeating things on a very elliptical orbit with the sun here. He calculated the period of this supposed orbit of 70-something years and predicted that it would show up in, I think it was 1757 or 8. It was after Halley died that it showed up. He did not live to see the appearance of his comet. But when it showed up, they're going, hey, look, a comet. Hey, didn't Edmund Halley say that was going to happen? Gosh, he sure did. Let's name it after him. So ever since then, it's been named after Halley. So that's quite a thing. The prediction of a disaster was made based on gravity. Oh, but there's so much more. Kind of zipping up to more modern times, orbits. I mean, we put things in orbit, you get them going fast enough, and you're falling, and you can't get down. And that's what orbiting is. I want to make a point kind of clearly here. When you're orbiting, you are falling. You are not weightless, not in the Newtonian sense. There's a sense in which you can use the term weightlessness. I'm not going to argue with NASA over this really, but basically when you're in space, in orbit, you are not weightless because otherwise you wouldn't be orbiting. If you were weightless, you wouldn't have a force on you, and things without a force on them go in a straight line at a constant speed. And obviously orbiting spacecraft don't. You weigh almost as much in orbit as you do on the ground. So why are you floating around in a spaceship? Because it's falling with you. If you're in an elevator and the cable broke, you'd be weightless. You'd find out soon enough you weren't because you'd hit the ground. But here, you get fall, and not hit the ground. So anyway, we first we, in this case being the Soviets first, on October 4th, I think it was, 1957, put Sputnik in orbit, and it was a big deal. Soon after that, the United States put things in orbit. Soon after that, the Soviets put people in orbit, dogs and monkeys, and we did too. And then, so we got good at orbiting. And then, back in 1961, Kennedy said, let's go to the moon. And he meant it. And we did. And when you go to the moon, you got to get way far away from the Earth, because if this is the Earth, the moon would be like way out that window somewhere, really far away, 60 Earth radii away, 30 Earth diameters. So how do you do that? Well, there's a thing I want to mention briefly. There's that saying, what goes up must come down. I mean, gosh, let's see. That came down. You've always seen things that go up come down. But what if you went up real fast? Well, then you know what to do. You draw a little V versus T graph, you go up higher, like that. But there's this thing. Okay, let me see if I can explain this with a silly analogy. Let's say, if you were here, I would ask a poll. I would ask you this question. And several of you would say, oh, yeah, me. The question was going to be, when you were a kid, or recently, did you ever try to run away from home? You run away from home. Your parents did something you didn't like, let you do something, put you on restriction, whatever. You're all mad. So you pack you a bindle, the little stick with the little bag on the end. I don't know if you really do that, a little oboe stick, whatever you call it. Anyway, pack up and you run out the door, never to return. Except you didn't you? Well, imagine you run out the door and your mom's calling you to come back. Come back, come back. They can start trying to lure you with I'll make your favorite dinner, mac and cheese. And you hear it. You do hear it. And it does exert a little pull on you. And you're thinking, that would be good. I'm not sure what I'm going to eat tonight otherwise. And mom's mac and cheese is pretty good. It puts a little bit of a tug on you. But you got a lot of momentum. You are running away. But you hear the voice calling and calling. As long as you're not running away too and fading with distance, I forgot that. So as long as you're not running too fast, mom's voice will not fade too much, and you're not running that fast anyway. It's enough, and finally you turn around and you go back home and have your dinner or whatever. I don't know if they welcome you back or you're in trouble worse than ever. But what if you're running away a little too fast, where not only are you harder to stop because you got all that momentum, but also you're getting so far away from home so quickly that mom's voice is fading fast and you can barely even hear her anymore. It might be that you will never come home. Now, the analogy, of course, has to do with throwing something up from a planet. Like here's your planet, and you throw a rock up. And yes, that's up. Away from the center of anything is up. That's up. That's up. That's up. That's up. That's up. You know, all these directions are up because they're away from the center. Anyway, you throw a rock fast enough, it's going to slow down. Generally, it's going to slow down and then come back and hit the ground. But again, there is a magical speed called escape speed, or escape velocity, some call it. Escape speed, at which you will never come back. You'll go away and you'll always slow down, but not enough to stop. It's one of those asymptotic things. Your speed will approach some lower and lower speed, but never really stop, never turn around. I'm going to go ahead and tell you a formula for escape speed. I might hold you responsible for it. I'll put it up here just in case. You remember how orbital speed was for a circular orbit was the square root of g times the mass of the planet over the radius over how far you are from it? Remember that? I'm not going to derive it for you, but it turns out escape speed is the square root of 2gm over r, which is about 1.4 times that. I'll just tell you, when I was a kid and I was paying attention to the space program, I knew all about the Apollo missions. I knew that you had to go about 17,500 miles an hour to get into orbit, low Earth orbit, just, you know, a couple hundred miles above the surface of the Earth. I also knew from watching Walter Cronkite, that's the way it is. Doesn't mean much to you, does it? Oh, well, ask your parents, well, your grandparents, I don't know. Anyway, I knew from watching TV that you had to go 25,000 miles an hour to go to the moon. I did not know at the time that that was the square root of 2 times the other speed, but it is. So to go to the moon, they had to reach escape speed. Then they had to go into orbit around the moon. Then they had to descend down to the moon, then take off from the moon. Then they had to reach escape speed from the moon to come back to the Earth. And when they fell back to the Earth, they fell into the atmosphere going roughly escape speed. Because what goes up at about escape speed comes down at about escape speed. 25,000 miles an hour. That is really fast to hit some air. It is intense. In any case, so now you know there's this thing called escape speed. And you know a little bit about the space travel, sort of, kind of. Oh, I wish we could spend more time on that. In any case, but wait, there's more. Something else, kind of, something a little bit down to earth here. You surely know, I think you've noticed, you know, you go to the beach, and sometimes you get to the beach and the water is kind of way out there, and other times it's kind of up here. I'm not just talking about the waves crashing, I'm talking about the tides. Don't confuse tides and waves, or tidal wave. I'm talking about just whether the water's up kind of high or down kind of low. I think you've noticed it. I mean, you just like, gosh, our beach chairs were there just this afternoon, and now look, we're out for a walk, and the beach chairs would be gone if we'd left them, you know, or look, the tide went out. Now there's all these shells we can pick up. All these little critters got left behind, you know, the little shells did. So you know about the tides. People always knew about the tides. Galileo tried to come up with a theory about the tides, and it wasn't right. I don't even remember what it was now. And they have competing theories. But Newton explained them. I'm going to explain the tides. I'm going to do it kind of quick, kind of one time. I need to recharge here for a second. So, the tides. Okay, here's the Earth, and here's the ocean. I made it way too deep. Way too deep. Here is the moon. Yes, the moon's got something to do with the tides. It does indeed. So here's the moon pulling on the oceans. And you know what you might think? I'm going to draw what you might think, and it might be wrong, but I'm going to draw what you might think. You might think moon has mass, water has mass. Masses pull on masses. Moon pulls on water. Moon pulls water off towards moon. So the ocean might logically be stretched and pulled over towards the moon a little bit. And if that were true, then this person standing here would be neck deep in water. Of course, he's also about 5,000 miles tall. But anyway, he's up to his neck in water. Whereas this person over here is only ankle deep in water. Maybe they're the same person. Maybe it turns around and you go from neck deep to ankle deep and back that way the next day. Moon moves a little bit, but not a whole lot today. You know what? That ain't the way it is. Wrong. Look, wrong. Why did I show you something wrong? Because it makes more sense to most people than the thing that's right. That's why. Let me show you what's right. That's not what happens. Here's what happens. If you've really been to the beach, most beaches, and it does vary some, but really, the bulge is in both directions at the same time. These people are neck deep in water, and these people are ankle deep, and they could all be the same person roughly 6 hours apart as the Earth rotates. This could be at noon, and this is like 6 p.m. maybe or something. That could be the sun. You know, that could be the sun. It could be the moon or the sun. Anyway, this is midnight. I'm not saying that high tides happen at noon and midnight necessarily. Depends on the moon. But in any case, you see how you could go through different tides. Question is, why? Would there be a bulge both towards the thing pulling on you and away from the thing that's pulling on you? Okay, this deserves a longer answer, but I'm going to kind of cut to the chase and give the quickest, simplest one I can. You see, the Earth is not being held on a big popsicle stick. The Earth is falling towards the moon too. And the moon is falling towards the Earth. And they keep missing each other. It's called orbiting. In any case, it's not like only water is pulled. The Earth itself is pulled. Let me show you what causes the tides, essentially. There's different ways to say it, but this is the best explanation in my mind. The part that's closer gets pulled the hardest. This is closer. There's a r squared in the denominator, so it gets pulled harder. The Earth is pulled too, just not as hard. So this bulge is because the water gets pulled away, preferentially away from the Earth. Both are pulled on, but the water's pulled more. So it goes more towards the moon. It builds up a bulge there. But look, this poor water back here, so far from the moon, kind of gets left behind. And the Earth is pulled away. The Earth is pulled away from the water. So here it's the water kind of a little bit leaving the Earth behind. And here it's the Earth kind of leaving the water behind. And it makes a bulge on both sides. You get tides both when the moon's up high and when the moon's down as low as it gets. About every 6 hours, or a little more, because the moon moves around a little bit during the day. It's a little more than 6 hours between the high tide and the next low tide and so forth. By the way, the Gulf of Mexico is weird. It's got some funny ways the coastline goes and messes the tides up some. Most places, they'll act like this. You might wonder about the sun. Can the sun do it? Sure it can. The sun has an effect on the tides. That could have been the sun. Could have been the same picture. But it's the moon and the sun. What if they team up? What if you get the moon and the sun? Terrible scale there. This is not even remotely to scale. But if you have the moon and sun and the moon there, that would just do it more, right? Stretch it out more. You'd be right. You'd be right. Here's what might surprise you. That's at new moon when they're in the same direction. What if it's full moon and the sun's on the other side? If the moon and the sun are on opposite sides? Think. Okay, by now somebody would have said that when they're on opposite sides, it makes less tides. Nope, it makes more tides just like this. Because see, if the bulge is in both directions, then being both on the same side stretches you a lot in both directions. And being on opposite sides, I mean, each of those stretches you in both directions, so it's just lots of both directions. So you get high, extra, super duper tides called spring tides at both new and full moon. What about, do you ever get tides that aren't very impressive? Yes, you get them when they're at right angles, like if the sun was up here and the moon was over there. One of them's trying to stretch it this way. The other's trying to stretch it this way, and it kind of doesn't stretch much. Who wins? Well, on one hand, the sun's way more massive. On the other hand, it's really far away. If you calculate the force, it turns out the sun pulls harder. But the force itself isn't what makes the stretching. It's the differences in the force. The sun is so far away that one side of the Earth versus the other side of the Earth don't make a whole heck of a lot of difference to the sun. Whereas the moon, though it doesn't pull as hard, pulls fairly differently on each side. So the moon actually has more influence and kind of wins. Oh my goodness, that deserved more time than I gave it. By the way, the word for the tides when they're at right angle, neat. I've never seen the word neat anywhere else in the English language except to describe tides. The big tides are Spring tides. Look at that. Newton's explained the tides that all the ancient mariners knew about, you know. Oh my gosh, we are not done. What are some more wondrous things about gravity besides explaining the tides? I wonder if you ever wondered this. You know, we talked about how the Greeks love circles, you know, they're all into that. They thought heavens are perfect. You ever notice planets are kind of round? The Earth is mighty close to round. The sun is awfully close to round. You look at different planets, except for Saturn having those big ears, they're kind of round. Why would they be round? Why aren't planets, stars, planets, they're all kind of round? Why wouldn't they be cubes or something? And why are they there in the first place? How'd they get there? Well, the hand of gravity. Think about it. If say a bunch of people really all liked each other, a whole bunch, when they tend to gather together in a crowd. If they were able to gather outdoors on a big field or something, they'll just love each other. They're just besties. And that they would all get as close together in some sort of huddle as they could. What would it look like from up in the traffic helicopter that's spying on them for some reason? They would make a circle, wouldn't they? And what if people could fly? What if they could just float around, maybe live in a space station? What if a whole bunch of people liked each other then? Every one of them likes everybody else. What kind of huddle do you think they'll make in 3D? A sphere, because that's the best way to get all as close as they can. And that's what planets are. Planets are where a bunch of stuff in space, a nebula, a bunch of like smoky, gassy, cloudy stuff and junk, all loved each other and packed together to make a pile called a planet. And for that matter, really big piles of gases that packed together became stars. And why do the stars shine? Now, if you read that, if you read up on why do stars shine, you'll find they do this amazing thing called nuclear fusion down in the core. It is a big deal. Nuclear fusion is where stars get their energy in the most direct sense. However, why did they ever resort to that? Why did they ever do nuclear fusion? The answer is because the mighty hand of gravity drew all this material together because of its own self-love, you know, and packed it so hard. You know, when you compress a gas, I don't know if you know this or not. One time, I remember pumping up a bicycle tire in the basement right down there. I was pumping up a bicycle tire, and I noticed when I shoved the pump down here, the end of the pump got hot. It looked hot to my hand. Didn't burn it, but it definitely felt hot. Maybe you've noticed that too. I might have thought it was friction of the piston with the metal sliding, but no, the piston never reached that point. This got hot because I compressed the gas. A star is where gases have been compressed by a mighty hand of their own gravity and got so hot, then in desperation, they did this weird nuclear fusion thing. So gravity makes the stars shine. Gravity makes the planets. It makes the stars shine. It makes the tides. It explains the heavens and the earth. It's a big, big deal, this universal law of gravitation. Now that I've made a whole, it gets better than that. It gets way better. I'll take it further. One thing is, this video may run a tad long because it's good stuff. Okay, or maybe I'll split it. Anyway, what else does gravity do? You know what? Newton was worried about something. Newton was worried about this. He thought if the universe had things in it, let's start with the super simple universe with just two things, just one thing and another thing. They would love each other, and they would, of course, fall together. And that would be the end of that, right? Obviously, the whole universe is not all falling together. So how do you keep that from happening? Well, Newton thought, I know how to keep this thing from falling to this thing. I'll just put somebody over here to distract it and pull it that way, and then it won't go anywhere. And now I've explained why that one wouldn't move. But I've only deferred the problem. Now, this is just like things in space, whatever, planets, clouds, whatever. This one would get attracted towards this one. And how do I fix that? I need another one over here to pull it this way. If you're thinking much, you might realize that this never ends. The only way to get the universe to stay the same and not collapse would be for it to be infinite. You'd have to have another object forever to keep that last object from falling toward this object. And it has to go in all dimensions. Basically, Newton had a need to think the universe went forever. This is getting too deep to finish with this video. So I'm going to make one more video after this, probably a little shorter, maybe, that gets really deep. It's going to get into the fate of the universe, black holes, stuff like that, and weird things. I'll shut up with this video for the moment.